Let b be the vector 3, 1, w be the vector 4i minus 2j, and z be the linear combination 2w minus v. Compute the unit vector that points in the same direction as z. To attack this, let's do this as two parts. Let's first figure out what z is itself, and then we'll worry about the unit vector bit. Now z is the linear combination of 2 times w minus v. For me, it's always easiest to do my linear combination calculations using the column component form of the vectors. And so let's fill those in right now. The vector w is right here. It's the vector 4i minus 2j, which means that its components are 4 and negative 2. The vector v is right here. Its components are 3 and 1. And so now we've written this in its column component form. Now we're ready to compute. The first thing we have to do is scale. The first vector needs to be scaled by 2, which means we just scale each of the components by 2 to get the vector 8, negative 4. We also have to scale the second vector by negative 1. Scaling each of those components would get us the vector minus 3, minus 1. And then we can add these two vectors together. Now remember, vector addition is done component-wise. So we would add across the top components to get 8 plus negative 3, and along the bottom, or second component, to get minus 4, minus 1. Which gives us a grand total of the vector along the first component, 5, along the second component, minus 5. And so that's our vector z, the vector 5 minus 5. Now let's focus on the unit vector. The easiest way to get a unit vector who points in the same direction as z would be to start off with the vector z and to scale it, and the appropriate scaling would be to divide by its length. So all we need to do is find out how long z is, and then we'll scale the vector down by that, and we'll have a unit vector. So let's do a quick calculation. The length of z is going to be the square root of the sum of the squares of its two components. So 5 squared plus minus 5 squared. That means we're going to have the square root of 25 plus 25, or the square root of 50. And 50 can be simplified to 5 root 2. So there's the length of our vector. And now that we know this value, we can substitute it up here to get a unit vector by taking the vector z, 5 minus 5, and scaling it by 1 over the length of z, 1 over 5 root 2. If we do the scaling, we would have, for the first component, 5 times 1 over 5 root 2, and for the second component, negative 5 times 1 over 5 root 2. And we can now make the cancellations and come up with the vector 1 over root 2, negative 1 over root 2. And this might actually be a little bit easier to read in its row form as the vector 1 over root 2, minus 1 over root 2. And so there's our unit vector who points in the same direction as z. This isn't the only way to solve the problem, and there is a different way that we could compute the same unit vector, which is a little bit more trigonometric intensive. Let's give that one a shot as well. Let's start by sketching the vector z. So here's a set of coordinate axes. The vector z goes 5 units horizontal and then negative 5 units down. So it's a vector down here that points in quadrant 4. It's clear that since these two sides are the same, this is an isosceles triangle, which means this must be a 45-degree angle. So our unit vector u is just the unit vector who points at a negative 45-degree angle. Using basic trig, such a vector's first component would have to be the cosine of that angle, and its second component would have to be the sine of that angle. That's just the unit circle definition from trig. Well, the cosine of a negative 45-degree angle is 1 over root 2, and the sine of a negative 45-degree angle is negative 1 over root 2. And once again, we recover the same unit vector that we had before.